Okay, so good afternoon, everybody. Sorry for being so late. We had a technical problem, but hopefully it is done. So let me introduce you first, CMCC, the Centro Euro-Mediterraneo sui Cambiamenti Climatici. We have a new webinar series on oceans, sea, coastal and inland waters, inaugurated by Professor Maza from Cantabria in Spain. Okay, so please, can you go to the next one? So CMCC has a mission to investigate and model our climate system and all the interactions between society and physical system, the biogeochemical system, and in trying to help to overcome some of our critical issues for humanity. Next one, please. And CMCC is composed of 7 different localities in Italy. It has different laboratories in 7 different localities, and it's subdivided into 9 divisions, which, can you go next, please? Yes, 9 divisions, among others, climate simulations and predictions, ocean mapping and data simulation, and ocean predictions and application. Next, please. So topics of concern are, as we said, jobs and growth and their interactions with oceans, cities, coast, energy, and all the aspects of human activities and modify the environment. Next, please. Yes, so we have an office for communication, publications, event, and we have also education. Next, please. Yeah, to participate in the quality and answer session, please use the questions tab on the GoToWebinar control panel on your right. And then let's have finally Professor Maza tell us about nature-based solutions, one of the many important questions that we have to try to solve for the future. Thank you. Please, Professor Maza, start your lecture.
Okay. I hope you can all see me and hear me, and as well as my screen. So here is my talk. So first of all, sorry for the delay, and thank you very much, Professor Nadia Pinardi, for the invitation. And I think the audio is just repeating and repeating again. Okay, let's try now. So thank you everyone for attending the webinar. So I'm going to talk today about nature-based solutions for coastal defense, but specifically I'm going to show you some works that are dealing with experimental and numerical modeling. So okay, this is the outline of the presentation. I will start with an introduction just to motivate the different studies I'm going to show you. And then I will try to cover the main aspects that are linked to the 3 main vegetated ecosystems that we can find in our coastlines. Finally, I will finish with some future needs that, from my point of view, are important to cover in the near future. So just to motivate a little bit the problem, we all know that coastal zones are very vulnerable and they are highly populated. The problem here is that due to climate change, there is an increasing risk in these areas because of sea level rise or the changing in frequency and intensity of the storms. All that risk is producing some economic consequences. The main hazards are the flooding and erosion that we can have in some cases in our coastal areas, and those are producing economic losses as well as human losses in some cases. So because of all that new situation that is hitting us now due to climate change, we are starting to think in the last several years, we have been starting to find or trying to find new solutions, more sustainable solutions that are actually eco-friendly, and they are these ones called nature-based solutions that are actually based on using the natural ecosystems that we can find in our coasts. So as coastal engineers, we know how to design great solutions. Those solutions have been studied for many, many years. And if we want to design a great solution in order to provide a specific protection service, we have the guidelines, recommendation, and tools to do that. But that is not the case if we want to deal with green solutions or nature-based solutions for coastal defense. In this case, we are using these ecosystems, but the problem is including more disciplines in this case, such as biology and ecology, because we are dealing with living organisms. So that makes the problem even more complicated. And this picture is just trying to show you that we need to work all together in order to find and to give an integrated solution if we want to implement this type of solutions in the real world. In this talk, I'm going to talk only about this area of the graph. Specifically, I'm going to be focused on the hydrodynamics. Why? Because the baseline of all this problem is flow ecosystem interaction. So flow ecosystem interaction is actually driving the protection service that these ecosystems are providing us. But this flow ecosystem interaction problem is very complex. We are dealing with different dynamics, wave currents, a combination of both. But on top of that, we are also working with flexible and rigid vegetation that is different biomechanical properties of the ecosystem that can be submerged or emerge. So in the end, what we are facing here is a huge amount of nonlinear processes that we need to understand and parameterize in order to implement this type of solutions, in order to know how much these ecosystems can protect us. So, as I said, the main objective is to better characterize this flow ecosystem interaction. How? In this presentation, I'm going to show you two different approaches, an experimental and numerical approach. For the experimental approach, I will show you different types of studies, some dealing with scale models, some dealing with real scale models. And according to the numerical approach, I will be focused only on small scale models, solving Reynolds average Navier-Stokes equations. Why? The whole picture is this one. And I'm including this slide because I want to emphasize that both approaches can be applied jointly in order to give a more integrated solution or a more complete solution. So according to the experimental models, we can have scale and real scale models, okay? And according to the numerical models, I said that I'm going to be focused on small scale models. These small scale models rely on a good validation, because when you are developing a new numerical model, of course, you need to prove your model is working well to be sure that you can apply it. So most of the numerical models, especially at the small scale, are validated by using experimental data. Why? Because experimental data is obtained under controlled conditions and detailed measurements can be taken. So those bunch of data are very useful to validate our small scale models. However, if we want to face a real problem at a larger scale, if we want to solve a whole ecosystem dealing with several kilometers or even working at a global scale, we need to go for macro scale models. But macro scale models cannot solve all the small physics that are produced in this flow vegetation interaction. So what we need is to parameterize those physics in order to infer what is going on in that interaction, although we are not solving all the small physics inside. In order to do that, what we do is to try to find new formulations and parameterization of those physics in order to feed these macro-scale models by using those data from the small-scale models or directly from our laboratory experiments. So by this whole view of the numerical modeling and experimental modeling of this type of solutions, I'm gonna go through some details. Before that, just to let you know, I'm gonna be focused on three main ecosystems, the three main vegetated ecosystems that we can find in the globe: seagrasses, saltmarshes, and mangroves. Here you can see the distribution and how they are present in most of the coastal areas. So then, if we are able to better parameterize and quantify how these ecosystems are providing a coastal ecosystem service of protection, we will be able to continue the work at a larger and more applied scale to provide with new guidelines and recommendations, or even new tools that will be very helpful, not only to quantify the protection service that these ecosystems provide, and for example, to protect them, but also to plan restoration actions in those areas where these ecosystems has been damaged. So just starting with the first one of these three vegetated ecosystems, I'm gonna start with the seagrasses. So the organization of the talk is all the time the same. I'm gonna just highlight main characteristics of each one of the ecosystems, and then I will show you just a small pieces of work facing those type of characteristics and problems. So according to the seagrasses, what we are facing here is the interaction of flow with flexible and submerged vegetation. So the main objective of this piece of work that I'm going to present was just to get a new model that was able to quantify this wave attenuation. I want to just highlight that this species that you are seeing here is Posidonia oceanica. You will see that is the one that is going to be studied in the next. So the first step to get this numerical model to quantify the attenuation provided by this seagrass was to have a literature review, and what we were obtaining was the data from these two experiments in the lab that were performed previously, and they were used in order to validate the numerical model that I will show you in. But also we were performing some new experiments in the lab, these ones in here, just to quantify with a synchronized measurement of the motion and the flow to get how the vegetation was moving under the waves. At different wave phases, we were able to get the vegetation motion. Just to point it out, these mimics were obtained considering the biomechanical properties of Posidonia oceanica, the seagrass that I was showing you in previous slide. That is, that the biomechanical properties, including the modulus of elasticity, was considered to create this mimic. In this case, real vegetation wasn't used because Posidonia oceanica is highly protected. So we were just trying to replicate the real conditions as better as we could. With that, we needed a new formulation, a new analytical model that was able to represent the motion of these seagrasses under the waves action. So this equation in here, including inertia, damping, restoring, drag, gravitational, and pressure gradient forces, was used in order to induce this motion of the vegetation. The important point here is that this symbol is representing the motion of the vegetation. So what we have in the main force driving this flow vegetation interaction, the drag force, is the relative velocity. This relative velocity is just the fluid velocity minus the vegetation velocity. That is the actual velocity that the vegetation is feeling when the flow is just interacting with that. In order to get this relative velocity, the motion of the vegetation was solved, assuming small deformations and this vertical linear integration along the vertical to get this displacement along the vertical. With that, differentiating this, deriving this motion as a function of time, we were able to get the velocity and then the relative velocity that was used to get the drag force. So all those variables were used to solve this motion of the plants. With that, then we use a numerical model. In this case, it was a two-dimensional Reynolds-Navier-Stokes model, two-dimensional in the vertical. You will see that in the next slide. It is called IHCantabria. So what we introduced was in the momentum equation a drag force as a sink of momentum in order to induce this dump of energy that is produced by the vegetation. Of course, according to the turbulent closure model, typical of RANS models, in this case, we were using a K-epsilon model, and then we were introducing two extra terms as a function of the vegetation properties to introduce the production and dissipation of turbulence produced by the plants. The whole numerical schemes was, in summary, as this. We were solving all the fluid properties. With that, we were resolving the motion of the vegetation, as I was telling you before. With that motion, we were able to get the relative velocity, and then we were moving to the next step, where we were introducing in this drag force that relative velocity to induce the sink of momentum that is producing wave damping. So here is just an example of the model. In these panels, we can see the validation. We have the solid line is the numerical model. The dots are the experimental data from the literature. This is just wave height along the middle. And then below, what we have is just the velocities. Velocities offshore the vegetation and inside the vegetation. So we have the minimum, mean, and maximum velocity profile for the waves. Here we have positive velocities, wave crest in red, wave throw in blue. What is important in here, a process that should be considered when we are dealing with this type of submerged vegetation, is that we have a skimming flow, an overshooting in the velocity profile just on top of the vegetation. This line is just deploying the end of the vegetation. Actually, you can see it in here. You can see this darkest red color that is produced on top of the vegetation. So this skimming flow is very important if we want to resolve in detail the physics that are produced in this type of submerged vegetation. Also, I want to point out that you can see here how, sorry, I can plot it here. You can see here how velocities and wave height are decreased along the middle. That is that the middle is producing wave attenuation. That skimming flow that I was mentioning before, and that should be very important depending on the problem we want to solve, is highlighted here. You can see this is just for fun. These are passive particles. But if we imagine that these particles could be nutrients or oxygen, you can see that, for example, the ones that were on top are moved very quickly till the end of the middle. In this case, I'm just comparing a continuous middle and a middle with a gap, and you can see this nice recirculation of nutrients or passive particles that can be produced in case we have that type of gap. So just to finish with seagrasses to move into the next ecosystems, just to highlight the main outcomes of this type of vegetation when we try to model it, the first outcome from this study was that a new drag coefficient was obtained as a function of the Reynolds number. This drag coefficient was calibrated considering the relative motion between the vegetation and the flow, because we are dealing with flexible vegetation. But an important aspect in here is that we can also infer the same wave damping by considering a model that is including in the momentum equation the common or the typical drag force formula that is considering the velocity of the flow instead of the relative velocity that is produced when we have flexible vegetation. That is, modeling the flexible vegetation as it would be rigid. So if we are dealing with those type of models, instead of using this drag coefficient that has been calibrated for flexible vegetation, considering the relative motion, what we need to do is to calibrate a new coefficient, drag coefficient, that is going to be different and is going to take into account, in a way, this motion by putting in this equation a different coefficient that will give us almost the same drag force, and then we will have the same sink of momentum producing wave damping. So if you are dealing with flexible vegetation and you want to model it, first review the type of equation that is implemented in your model, and then you will need to use the drag coefficient associated to the specific drag force that is implemented in the model using the relative velocity or the flow velocity. By moving to the second vegetated ecosystem, I am going to present the work of saltmarshes. Regarding the saltmarshes, well, for those of you who have been performing field campaigns in this type of ecosystems, you will see something like this. That means that we can find different species just living very close to each other. But the point, for example, here we have Puccinelli and Arimione. Those species are actually very different if we think or if we measure their biomechanical properties. The same if we compare them to Spartina. So in the same ecosystem, in the same area, we can have different species with completely different biomechanical properties, and those properties will induce different wave attenuation or flow energy attenuation. So that is very important when we are dealing with saltmarshes. Also, these ecosystems are living in the intertidal areas and they are subjected to waves and currents, and both combined at the same time. And since they are in the intertidal area, they are under different submergence ratios. So the main objective of the study that I am going to present was to better understand the main parameters driving this flow energy attenuation in these complex ecosystems. In order to do that, real vegetation was used to avoid any scale effect, any parameterization effect of the properties of the vegetation. Real vegetation was tested. In this case, two species with completely different biomechanical properties were used. The first one was Spartina anglica, which is pretty stiff, and the second one was Puccinelia maritima, which is actually very, very flexible. They were grown up from seeds, and as you can see, it was a very tough work because we were growing a total area of a circle of 6 meters of diameter. So the whole process took months, but in the end, we were able to grow them and to test them in the basin under waves and current conditions, considering different water depth. So here you can see how the vegetation was introduced in the basin. So this is the Cantabria Coastal and Ocean Basin. It is a huge basin. This is just 6 meters of diameter, okay, the circle. And as you can see, the boxes where the vegetation was grown up were located at an elevation in such a way that the ground of the boxes was at the same level as the basin bottom. These wood elements were introduced to ensure a smooth transition between the basin bottom and the vegetated area. And here in this structure, different devices such as fixture, phase measure gauges, and ADBs were located to measure the flow properties. So these two species were tested under waves waves and currents at the same direction, and waves and currents in the opposite direction. So different tests were tested considering these three combinations. So here you can see an example of the fitting of the damping coefficient for the three different conditions. In blue, waves and currents following in the same direction. In black, only waves. In red, waves and currents flowing in opposite direction. So you can see how the beta, the damping coefficient, this is wave height, is different when we are adding currents in our waves, which is expected, right? But that was one of the outcomes, those bunches of damping coefficients for waves and currents in different directions. So another important finding from these experiments was this one. The two different vegetations were tested under different densities. Puccinellia, that was very, very flexible and extremely dense, was tested considering three different densities. The different densities were obtained by cutting part of the plants in this way in order to avoid any damage on the other plants that were remained for the following tests. For Spartina, we had a lower density, and then only two densities were tested. In the end, what we had was 5 different combinations of vegetation species and density. That means that if we talk about standing biomass, which is the weight of the vegetation per unit square area, we had 5 different points. And what was very important, or a very nice finding in here, was that if we plot, this is biomass, if we plot the damping coefficient obtained for each one of the different tests, that is the same wave conditions or wave and current conditions, but the 5 different values of biomass. If we plot this damping coefficient as a function of biomass, what we found was a linear relationship between the damping coefficient and the biomass of the ecosystem. This is very important and relevant because here we have only 5 points. I know they are only few, so this should be explored further. But if this can be extended to more species and densities and values of biomass, that means that we can obtain this damping coefficient as a function of the biomass of the system. Actually, now I'm working on trying to find this for more species, and let's see what happens. But it could be very, very relevant because even for waves and current conditions, you can see that the linear relationships are still there. So since we had a bunch of experiments where the damping coefficient was measured and all this attenuation was measured, a new analytical formula for wave and current conditions was obtained. Here we have the analytical study. I'm not going to go through the details, but this study was just based on a conservation of energy equation. And then in the most important aspects of this equation or of the derivation of this drag coefficient for waves and currents was that the deflected length of the vegetation was considered. It was a way to include the flexibility of the vegetation under different conditions in the equation. For example, for Puccinellia, that was very flexible. When we had only waves, it has a huge buoyancy force, so it was just moving like this. But when we had waves and currents, the plant was deflected in the current direction, and then it was moving just up and down according to the passing wave phase and wave flow. However, when we were, this deflected length was introduced in the equation. And another aspect that was very important to derive this equation was that we were considering the dense conditions that we tested in the lab. These high density cases produce flow diverging. The flow was diverted if the vegetation was covering the entire water depth. Currents were just moving around, while the waves were passing on top of the vegetation. However, if the vegetation was submerged, the currents were diverted in the vertical. So we had, instead of a horizontal flow divergence, we had that in the vertical. That was influencing this wave and current interaction with the vegetation, and it was considered in the formulation. That formula was used afterwards, or it can be used, for example, to perform this type of numerical modeling of the experiment. And then, for example, to extend the results to some conditions that weren't tested in the lab. So the main outcomes from these experiments, or from this study on saltmarshes, was that first, we need to care a lot when dealing with experimental modeling or numerical modeling on the properties of the vegetation. Here you can see the Puccinelia that is completely lying down on the floor because it was very flexible. And here we can see the Spartina species. They were completely different according to the biomechanical properties, and we could see that the effect on the flow attenuation was also different. So that should be considered when performing experiments. That is why usually we use mimics. But if we are using mimics, we need to be sure that they are produced and they are mimicking in a correct way, proper way, this type of properties that we can even see by the naked eye. Why are we using mimics? Because performing experimental campaigns using real vegetation implies a lot of effort. So we were a huge amount of people, we were working a lot to perform these experiments, and finally everything went well. But when you are working with living organisms, you never know. So that is also something that should be considered when planning an experimental campaign. And in terms of wave attenuation, that is the main aspect to quantify this coastal protection service, we have seen that the standing biomass can be a key parameter driving this type of wave attenuation. And also we need to consider the deflected length and the flow divergence that can be produced when we have these wave and current conditions flowing at the same time. And with this, I'm gonna move into the last ecosystem. So mangroves. Well, mangroves are pretty different to previous ecosystems, mainly because they can be considered rigid under the flow action, at least mature trees. They are emergent and they present completely different morphologies depending on the species. So the first step or the first study I'm going to present here is just a numerical study that is considering these elements as a rigid structures, just to check how the flow is interacting with them and to check how the individual's distribution is inducing different or not attenuations. So this model, the model that was developed inside IHFOAM. That is a part of OpenFOAM, the open source tool that is multidisciplinary. In this case, IHFOAM deals with waves and currents and coastal processes such as porous media or vegetated flow that I am presenting here. Two different approaches were considered. In the first one, all the individual elements were introduced in the domain such as solid boundaries. In the macroscopic approach, the vegetated area was introduced as an area where this momentum equation, where the drag force is again introduced as a sink of momentum, was resolved. So how we proceed when we are implementing a new numerical model? Validating the model. So in order to do that, we use these experiments, one et al. From 2011 from the literature. In these experiments, different arrangements of cylinders were tested under different solitary wave conditions. Here you can see the validation of the two approaches. Both were giving a good, very good estimation of wave attenuation along the field. What were the main differences? For the direct simulation approach, in which we are introducing the individual elements as solid boundaries, we didn't need any calibration parameter. For the macroscopic approach, where we are adding this drag force in the momentum equation, of course, we need to calibrate the drag coefficient in order to induce the wave damping that we observe in the lab. So we need for that calibration coefficient. But what is the advantage of the macroscopic approach then? Well, the direct simulation approach is more than 3 times expensive than the macroscopic approach in terms of computational effort. You can imagine that the mesh needed to resolve all the individual elements and to properly introduce them in the numerical model and the turbulent closure model is the cells are very, very small. So the computational effort is very huge. So if we want to resolve wave damping, we can go for the macroscopic approach, but we need to have an estimation of the drag coefficient that we need to introduce in the equation in order to be sure that we are inducing the wave damping properly. Once producing this model, different aspects were studied. One of them is the one I'm going to present here, was the distribution of the individual elements. So here we have the uniform distributions according to one experiment and the same amount of cylinders distributed in the same area, but randomly. So wave damping was compared in the different cases. So here we have wave damping for uniform.
Sorry, Maria, to interrupt you. Just very quickly, I wanted to ask if Professor Pinardi could try to turn off the her PC audio because it's making some kind of echo.
Yes.
Yes. I hope she will be able to do so. Sorry to interrupt.
Is that okay? Okay. Is that okay this way?
I think so.
Yes, I think so.
Yes, I don't hear the echo anymore. Yeah, thank you.
Great, thank you.
Okay,
Thank you so
sorry.
No, it's okay. It's okay. So for
today, many problems.
No, it's okay. Don't worry. So yeah, well, this slide is just showing you wave attenuation along the vegetation for uniform and random distributions. So here we have the 3 different layouts or densities, and here we have the uniform distribution and the wave attenuation obtained for the random distribution along these 3 lines. As you can see, the wave attenuation was very, very similar in all the cases. That means that while keeping the submerged solid volume fraction in the uniform distribution and in the random distribution, we were obtaining the same wave attenuation, even with different arrangement of the individual elements. So that is very nice because that means that we don't need to know exactly the distribution of the individual elements, just the density and the mean diameter, if we want to infer the wave attenuation they produce. However, if we want to deal with forces or flow inside the meadow, flow velocities inside the meadow, then we need to care about the individual distribution of the elements. So here, for example, we have the velocity magnitude on the free surface at this time step for the uniform distribution, the same time step for the random distribution. And you can see in here how this dark red color represents that flow is focused in that area. This is actually linked to the different forces that are obtained for the random distribution. For the uniform distribution, we have a pretty smooth decay of the forces exerted on the elements. But for the random distributions, you can see that we have a scatter of the data that is linked, of course, to those flow patterns that are also shown here for the random and uniform distribution. So depending on how the individual elements are produced, there are some cylinders that are just getting all the flow focus in that area, and some other elements are just behind others, and they are feeling this sheltering effect, and they don't feel any force. So, of course, depending on what you want to resolve, you need to go for one option or the other. Another application of the model can be the study of different patchiness. Instead of analyzing the distribution of the individual elements, such as uniform or random, in this case, this study was performed in order to understand how patchiness, non-continuous vegetation fields, were influencing wave attenuation. The first step was to perform this in the lab. So the different cylinders in here were reproducing Avicennia pneumatophores. At least the geometry of these cylinders was designed according to the properties of this type of elements. 3 different configurations were tested: uniform, 8 patches, 4 patches, under the same wave conditions to get wave damping. A new parameter was obtained, the equivalent length. This equivalent length is actually the length of a continuous field that is producing the same wave damping as a non-continuous field as this one in here. So if we plot the wave damping parameter coefficient as a function, for example, of the relative wave height, for the 3 different configurations, these are emergent conditions, submerged conditions, we find different fittings. But if we apply the equivalent length in this axis, and we link the damping coefficient not only to the relative wave height, but also considering the length, the equivalent length, that is the length of a continuous patch that would produce that wave attenuation, we can see that the points for the 3 configurations are fitting the same line. That means that this equivalent length is a good estimator of the actual wave damping produced by these patches. Of course, the numerical model I was presenting before can be also applied to this type of experiments. This slide is just to highlight that both experimental and numerical analysis are very, very linked to each other, and they can complement to each other. Like, for example, in this case, we are showing here the forces exerted on the individual elements that are very difficult or time-consuming to measure in the lab. So that can be another application. So what were the main outcomes of these 2 studies performed with cylinders? Well, first, that wave damping can be accurately obtained if we use the macroscopic approach that is cheaper in terms of computational effort, but we need to calibrate the drag coefficient. Then randomness seems to be not very important in terms of wave attenuation if we keep while maintaining the submerged solid volume fraction. And then the equivalent length can be very useful if we are dealing with, or if we are using numerical models that are reproducing the vegetation as a continuous field, and they don't have the capability of introducing individual patches. So instead of dealing with this, we can introduce in our numerical model this continuous field, and we will have the same wave attenuation. So that can be a useful parameter in terms of numerical model. And just to finish, I'm going to present you the last piece of work that is dealing with Rhizophora species. Rhizophora species are the most common ones, and they are characterized by these complex root systems. So as you can see, these elements cannot be equal to a cylinder. And also, they are usually used in restoration efforts. So they are very important to understand. It's very important to understand how flow interacts with them in order to plan these restoration efforts. So in order to do that, a parameterization of this geometry by Ohira et al. In 2013 was used, where the diameter of dress height was taken as the key variable to get this whole 3-dimensional layout of roots. Of course, these elements, this is more than 2 meters height, cannot be introduced in the lab directly at real scale. So scaling was needed. Broad similarity was used, and Reynolds similarity was considered in order to ensure that the weights behind the elements were the same. That is, the Reynolds number range in the field and in the lab were the same. So the first study was performed under unidirectional flow, and a new drag coefficient for this type of complex geometry for unidirectional flow was obtained. But then, at a larger scale, these elements were introduced in a huge flume that allow us to build a 26 meters long field that is 156 meters long at real scale, and to test them under wave conditions. Different waves and water depths were tested and free surface and velocities were measured, and as well as forces on these 9 black elements that are deployed in this display in this figure, with this arm that was designed for the experiments. So these are just a few of the results. I am just getting to the end of the presentation. So one of the results from these experiments were the dynamic forces exerted on the individual elements. Those forces are very important because, as you have seen along my presentation, the drag force is the key force parameter in physics that we need to better understand in order to parameterize flow vegetation interaction. So here you can see just a zoom of the forces exerted by a random wave train in these 3 elements. Also, wave damping was measured. Here you can see the wave damping for 3 different water depths, these ones, and these wave conditions. Which is important here is that the hydrodynamic conditions were tested twice. Why? Because we wanted to parameterize or to know how much the bottom and walls friction of our facility, how much wave damping were they producing. Because the dashed lines are actually the wave damping produced by the empty channel. That is the wave damping produced by the walls and the bottom friction of our facility. It is not wave damping produced by the mangrove elements. So we need to consider that when quantifying how much these elements are protecting us. In order to do that, the wave damping measured by the flume full of mangroves was obtained, and then we were subtracting the bottom and walls friction contribution to get this new damping coefficient that was the one associated only to the vegetation elements. With that, the drag coefficient could be obtained with this analytical formula for both cases, the same for the drag force. In the end, what we got was these solid lines were the drag forces for the 3 different water depths and different random wave conditions when considering the damping obtained by the flume full of mangrove without removing the contribution of bottom and walls friction. If we remove the contribution of our facility friction, we got these dashed lines. As you can see, they are much smaller. So are actually these dashed lines a good estimation of the drag force exerted on the elements? Well, we have the direct measurements, the measurements obtained directly on the individual elements. And here we have a comparison of those drag forces obtained analytically from wave damping by subtracting the contribution of the friction of our basin compared to the measured values. And as you can see, they are pretty similar. Actually, the maximum relative error was 12%. This is very important because measuring forces in the individual elements in the lab is very difficult. So, but measuring free surface is pretty easy. So this highlights that actually we can get a pretty good estimation of the drag force exerted on the elements by the wave damping, but considering always only the contribution of the individual elements. Bad news, we need to repeat our experiments twice, but that is something needed. And the last finding I'm going to show you is this one. This is just highlighting the idea I was telling you before about the importance of the submerged solid volume fraction when I was telling you about the random distribution. So here you can see a common fitting line for the 3 different water depths and all the different wave conditions tested in the lab. And we have the same fitting line for the wave damping obtained for all the tests as a function of the relative wave height and the submerged volume fraction for each one of the water depths. So that reinforced the idea of the importance of this submerged solid volume fraction and that as a key parameter to quantify the wave damping produced by the ecosystem. So this is just highlighting what I was saying before, and those are the main outcomes of this last piece of work. So just to conclude, I have been telling you some needs or important aspects that should be considered when we are dealing with numerical or experimental modeling. But that is just the baseline. That is the bottom of all what we need to do. If we will characterize this flow vegetation interaction, then we need to extrapolate this data or these findings to a larger scale, to a more applied studies, in order to move forward in the implementation of these nature-based solutions in coastal policies and management. So in order to do that, I want to reinforce the idea of multidisciplinary teams. If we don't have people who are experts from the different disciplines involved in these type of problems, we won't be able to give an integrated answer to this question. Only that way we will be able to provide with new guidelines, recommendations, tools to include these ecosystems in coastal defense policies and management and planning. And we also need to think or to consider that these ecosystems are also providing with some other ecosystem services, not only coastal protection or adaptation to climate change, the one that I have been covering a little bit today. No, they are also, for example, they are sinks of CO2, so they are helping to mitigate climate change, and they are providing with habitat, improving the water quality. So all those benefits should be also considered in order to reinforce the idea of this type of solutions and to tell coastal managers that they are actually providing with many different benefits. So I want to acknowledge all the different fundings that I had in order to perform these experiments, and of course, all the co-authors and contributors that made possible all these different studies I have been presenting today. Thank you very much for your attention, and this is my email in case you have further questions. I will be happy to take some now.
Thank you very much, Maria. Can you hear me now?
Yes.
Sorry about this inconvenient start, and I hope people have been able to follow this exceedingly interesting conference, which really looks into the future of what should be coastal protection. Now, I like your definition of the gray protection, which I never heard before. And can you tell us your evaluation? How good is the gray protection at this point in terms and with respect to some of your solutions instead? Can you tell us the numbers that I can remember, and then we can read the literature?
Yeah, so you mean in terms of, for example, the percentage of wave damping per
yes.
meter or something like that?
Yes.
Yes.
And maybe also with respect to damage, if possible, produced at the coast, if there is a quantification of that, because that's quite difficult, I guess. There's so much damage with the high waves, but then when the waves are dumped in one system or the other, it's clear that the damage is different. And so is it possible to quantify?
Yeah, so the answer is not general, in the sense that we need to consider the properties of each ecosystem in order to give a number for the attenuation that they provide. So that is why I think numerical models can help in that sense in order to be applied for case-specific cases to have a quantification of that protection. But for example, if we, like a last study that is not included here that I've been working on is about mangroves. So depending on the mangrove age, of course, the coastal protection they can provide is very different because they are growing and they are producing different amounts of wave damping. But an important finding was that actually there is a self-thinning process in this type of ecosystems in such a way that when we have young mangroves, we have plenty of them, but they are very small. When they are growing, we have less, but they are very big, but they are separated. In the end, with this idea of the submerged volume fraction, the submerged solid volume fraction, it is not so different if the water depth is not very big. So we can find some numbers of the protection or of the wave attenuation that this type of ecosystems can provide, even in a general way for one specific species. So for example, just to give you a number, because I'm just saying general stuff, for these experiments with the 26 meters long, that is 156 meters long at real scale, we were having, even for the higher water depths, we were having attenuation rates of more than 60% of the incident wave height. So that means that if we have, if we have, for example, a mangrove forest of more than 2 kilometers, for short waves, we will have an almost full damping of the incident wave height. But as I said, if we want to quantify one specific ecosystem, we will need to go and study that specific case to be sure that we are giving an accurate answer. That's why I think numerical tools are so important.
Thank you very much. We have so many questions. I have to start to read them to you.
Okay.
So we have the first one from Mariana Vidal from Plan Adapt in Berlin. Thank you for the great presentation. My question to Professor Maza are, have the presented findings been already used for parameterizing regional or global models to predict risk reduction on coastal areas due to different vegetation types? Yeah. And the second, could you name examples of how the findings could be coupled with socio-economic models to predict losses due to climate hazards in coastal areas? Okay.
So for the first question, I can say that we are now working on that, actually, because as future needs, I was actually pointing out that it is very important to jump from this small, more fundamental scale to a larger, more applied scale. And that is something that we are now doing in IHCantabria, because we have also experts on those type of aspects, such as risk, social and economic aspects, hazards, so risk evaluation and so on. So this small scale is just the bottom line to feed those larger scales. And now we are working on applying this type of knowledge on, for example, mangrove fields. Actually, in the past, we were also working on that combination. So I'm not an expert myself on that analysis, risk analysis, and so on. But there was an important project carried out in the Institute where they were quantifying the economical losses that we will be facing if we lost mangroves or coral reefs in different areas along the globe. So those studies are based on this type of more fundamental analysis. And now I don't remember exactly the question.
Well, we have to go because we have to get some satisfactions among the different questions. Yes, so here is a simple one maybe. Was the Seagrass model implemented in open form? Is the model open source?
Yeah, so the Seagrass model was implemented in IHCantabria, which is not open source, although we provide them to companies and so on with the training. If you are more curious about that, just go to IHCantabria.com and you will have all the information. So in open form, the general equation, the momentum equation introducing the drag force is implemented but the motion of the vegetation has not been implemented yet.
Yeah, I guess it's going to come next. So we have also somebody else having a question about the solid volume fraction. You mentioned earlier that a regular layout of tubes feels less force than a random layout of the same solid volume fraction. Is the relationship with solid volume fraction still linear for a regular layout?
If I understood correctly, I think it refers to the slide where I was showing, sorry, I can go there because I'm sharing here. So in this slide, I was showing that actually the uniform distribution was producing these forces. But when we had the random array, we have this scattering of the forces. So, but then when I was mentioning before the solid volume fraction and the importance of on the parameterization of the drag force, I also plotted these results, showing that we can actually get an estimation of this drag force by considering the global parameters of the vegetation, that is the solid volume fraction. So these forces are the ones that are produced inside the middle, okay? And it was obtained for the random distribution. For a regular distribution. For a random distribution, if we get a mean, as you can see in here, in here, you can see that all the scatter is around this mean value. So we can expect that the mean value of these forces will be very close to the uniform distribution. But that doesn't mean that we can obtain all individual forces as a mean. Because if we are dealing, for example, or we want to know if a tree is going to be broken under the wave action, we will need to go for this detail, getting all the individual forces to see if the threshold is passed. So I don't know if the question was in that direction, but yeah.
Yeah, we needed to go ahead. I mean, it was quite well represented by your slides. So how would you expect the sediment transport to affect your results, providing changes in water depth and also changes in vegetation density by trapped sediment?
Yes. So today I was just showing you flow vegetation interaction without including sediment. But now we are studying flow vegetation sediment interaction. And of course, sediment is influencing all the different parameters. But if the sediment motion is not extremely big, the wave attenuation is not going to be modified so dramatically, because the main source of wave damping in a vegetated area is due to the vegetation elements and is not produced by the bottom friction. However, if the bottom is changed dramatically, as I said, we need to consider that to quantify the wave attenuation, as well as if we have any vegetation elements that has been lost because the bottom has been eroded, of course. But that is another variable that I didn't include in the presentation, because if not, I could be talking 2 hours instead of 1, and that it wasn't the purpose. So
what we need to have these complex, high-resolution models. We have to find a way to put them inside our macroscopic models. Here, I have another question. What are your thoughts and recommendations on hybrid infrastructure solutions? What type
Yes.
of models do you recommend when studying these types of structures, infrastructures?
Okay, yeah, I believe that in the future, in the near future, those solutions are gonna be extremely relevant because ecosystems provide with a significant protection, but they are not the solution for everything. In many cases, we need to combine them with a traditional rigid gray infrastructure that maybe it could be more eco-friendly by considering different aspects, but it's gonna be a rigid structure. So I think the combination of both are gonna be giving a solution to specific problems, especially in cases where we don't have enough space to implement these soft solutions. In order to go forward in those ones, I would recommend to start by, modeling them both numerically and in the lab. Talking about numerical models, I would recommend models that have already implemented rigid structures with porous media and so on, and also vegetated fields. And that way, both solutions can be combined in the same numerical model to understand better how they are interacting with each other and they are providing a ecosystem, a protection service.
Yeah. Thank you so much. I have another question here that is interesting. All of them are interesting. What seagrass meadow coverage can attenuate waves down to 60%? What is the relationship between coverage, seagrass, and wave attenuation?
What is the relationship?
So can you give a number? Attenuation and coverage of seagrass.
Of coverage of seagrass.
Seagrass coverage. You know, how big are the prairies have to be? You showed something at the beginning. Yeah.
So you mean the length of the seagrass? Or,
well, this is talking about two-dimensional, not only the length, but maybe a large area, not two-dimensional size.
Yeah. Yeah, I mean, it depends on the seagrass. I can say that, for example, for this type of seagrass, for Posidonia, here we can see some numbers. Like, for example, by considering a continuous seagrass meadow in the lateral size, okay, just through the flow direction, we can see here that this was an 11 meters long seagrass meadow, if I remember well, at least more than 10, as you can see here. And here we had an incident wave that was something like 0.34, and it was decaying till 0.24. So that was a significant wave decay. But this is just for these specific wave conditions. If we check another different wave conditions, we will have a different percentage of attenuation. So I cannot give a specific number of the coverage that we need to have of seagrass to have a certain level of protection, because also it depends on the incident flow conditions. That would be more specific question taking time, just seeing the incident wave conditions of the area, checking the length and coverage of the seagrass, and then I would be able, I believe, to give a precise answer of this attenuation produced by the seagrasses.
Yeah, if I could also ask a question now. Have you thought of applying some of these drag effects on what we use normally to produce forecasts of waves at the coast, which is ocean wave spectrum models that have, yes. So do you have a formulation for the traditional wave average motion or wave spectrum motion for the effect of seagrass?
So yeah, for the seagrass, I didn't go into those analyses. I was just analyzing this wave damping as a function of the incident wave conditions, but without considering like energy spectra analysis in the sense of considering the attenuation at the different energy bands. Instead,
That's right.
I was considering was, for example, an irregular wave train following a Jones-Swap spectrum of an enhancement factor of 3.3 or whatever. And then with those spectral conditions, I was obtaining the damping, but I didn't have like a general formula to say, okay, the spectrum is gonna be damping in this way along all the different energy spectra frequency bands. So yeah, I cannot give that answer, but it can be inferred by introducing a damping of the energy following the traditional energy conservation analysis that is considering as the only sink of momentum, the drag force. So you have the whole spectral energy variation along a distance, and that is equal to the diminution of energy, the decreasing of energy produced by the drag force, the integration of the drag force times the velocity. So then that drag force can be included by considering the drag coefficient that I was presenting here.
Thank you. That's very nice. Thank you for the idea. We will talk more about this with you.
Okay.
Could you please have a physical interpretation on the effect of current presence on wave attenuation on seagrass? So this is the wave current effects coupled.
Okay. So the question was if I can comment on this?
Well, what is the physical interpretation of the effect of the wave current interactions?
Okay, so in this example in here, what we can see is that wave and currents following in the same direction were producing less attenuation than the ones following in the opposite direction. So in this case, what I can say is that it's not only a physical aspect of the wave and current interaction by itself, because we have the nonlinear effects of wave and currents, but it's not only that interaction, but also the influence of the vegetation. And for example, in these specific cases where we had dense meadows, it was very important to consider these diverging flow processes. When we were measuring velocities inside the vegetation, we couldn't find unidirectional components. We only had oscillatory components, that is the ones associated to the waves. So waves and currents following in the same and in opposite direction were actually affecting the incident wave condition. So the main aspect in here was that although here you can see that the incident wave condition or wave height seems to be the same, they are just non-dimensionalized by the incident wave height. So that is that the incident wave height was different when the currents were present. And then different wave heights are attenuated differently along the middle. So in this case, it wasn't only the nonlinear effects that we have between wave currents that are already there, and they are producing that difference in the incident wave height. It was also the influence of this diverging flow. So in the end, what we had in general was a higher wave height in front of the middle when we had currents in the opposite direction, because we had the waves, the currents in the opposite direction, and wave steepness was increasing. So then we have a higher wave height that was highly attenuated along the middle proportionally, okay, than when we have wave and currents flowing in the same direction. That was the main aspect.
And I should say the last one because we cannot take more of your time. You were very generous with us. But we have a question here that does wave height attenuation increase with increasing submergence ratio?
No. So attenuation is decreasing with increasing submergence ratio. If submergence ratio is obtained as the water depth divided by the it's a matter of definition. If we consider water depth divided by the vegetation height, if we have a submergence ratio of 1, it means that we have the full water column covered by vegetation. That means high attenuation. If the vegetation height is decreasing, we will have a submergence ratio bigger than 1, and then we will have a smaller wave attenuation because we will have only part of the water column occupied by the vegetation. So in the end, the important aspect is how much of the water column is occupied by the vegetation. And that is why I was showing you before this graph where emergent vegetation was producing a much higher wave damping than submerged vegetation.
So, I mean, everybody congratulations and thank you very much for this. And I personally would like maybe to extend also my thanks to this exciting future avenue that we have to save our planet. I think we should continue this and do more. So, if you don't mind, we will invite you in a few more months to give us the other news about these interesting techniques.
Okay, thank you very much, Professor Pinardi, and thank you for the invitation and organizing and everything.
Just to tell you, we had more than 300 listeners.
Oh, wow.
Okay.
That's great. Thank you so much for advertising that. Thank you.
Sure. Bye-bye. Thank you very much.
Okay, bye. Thank you.